So one screen will be a generator, and the other screen will be real EEG. So essentially, how do we know that synthetic EEG looks like real EEG? Well, if we go here, at the time, 10 seconds. On the left, we have simulated a synthetic EEG. And on the right, we have real EEG. And simply by doing this, I mean, if we just go into random, this is flicking through channels. This data has its intracranial 16 channel recording. Well, yes, this EEG has more delta to it. So, so you just add more delta here. No, that line is just thicker. That graph goes up to 50. So say if we had a 40, so say beta looks a bit wider, bit higher amplitude. So trying to replicate this spectrogram. Then we have alpha. It's also a bit wider. By the way, the width of those will depend on the filter order. We can make it if you go up to all the way up to 30 order, then they look sharper. So essentially, this is how much. So they look like if you look at the overall shape, they just look like a continuous shape. So maybe we can do this. Then we have theta increase. Yeah, there's a bit of a jump there in theta, and then delta is much higher. So does it look the same? Well, not really. First, there's some sort of rendering issues. Just the line is thicker than there, so you can't really see. And yes, potentially this one has some spikes in it. So the spikes would be in the lower component. And yes, this model is literally just taking white noise, band passing it into a certain frequency range, and then putting it together. So nothing fancy. Whereas in real EEG, you also have this potential spiking activity, like this one and that one, which what kind of looks like spike there. But yeah, this spike is just a certain frequency, some frequency component, nothing special there. So I guess if we narrow this down, there will be more things that look like spikes. I don't know what the frequency response of a spike. It's something to look into. Yes, so yeah, I guess a spike. Let's see if we reduce the window size. and find the spike. Look at its those spikes. I don't know. There's actually this particular sample doesn't have epileptic responses. Um, so there should not be spikes here. So there's things that look like spikes, and that's what its response is like. Yeah, filter order makes a huge difference. Um, so yes, it has essentially more of this. I guess something like 3 or 4. A filter order is fine. So you have this more of a low frequency component. And yeah, and that's what makes it look like spikes. So this will be. Does this look similar? No, I don't know. Oh, normally you filter EEG between like zero point 0.5 hertz to 30. So this one is obviously not filtered. You do that because you have a lot of baseline shifts. Obviously, this signal, a synthetic signal, doesn't have that problem. So in theory, you don't need to filter it to high pass 0. 0.5 hertz. But yeah, so this thing will generate something that looks more like spikes. So your window size matters a lot. How the thing looks like on the screen, but it will generate the same. You could get it to generate the same spectrum. So you literally could have this one matched to that, either manually or automatically. So I could translate this energy there, the power, into a slider up and down, and then create the synthetic EEG out of it. And yes, probably like EEG lab, things like that will have better resources. There's also another, so I actually want to try this next. There's another similar to EEG data generator publication, but back from 2018, University of Oxford. But then they're using EEG lab, so that's actually not a publication. It's just self-published thing. I don't know, but they're just talking about essentially how to use EEG lab, which yeah, I don't know if EEG lab. So they obviously, I don't know if you know, they have a MATLAB toolkit that I was using like ages ago, but yes, it has some limitations. Maybe now they're much improved, and maybe they also have MATLAB code, sorry, Python code as well these days. So yeah, in this paper, they yes, they use CG event response potential. So essentially, they're generating noisy EEG with like a standard. Is this a standard MATLAB function, or is it EEG lab function? Yeah, I do want to implement something similar. And yes, MATLAB will be easier to convert to Python considering it's text based. I don't know if Python probably has similar functions. Probably not in its main release, but right. So it is a EEG lab function. Yes, we used the EEG lab before standalone. They have now Python and things. Yeah, the other thing is that I would trust EEG Lab. It's been used for quite some time. Um, a, a lot of publications using it. And yeah, I wouldn't necessarily trust anything written in Python. So just beware of that. This guy's from the same. That's the publisher. This CG Lab people. But anyhow, so they generate, then they have noise, and then they have another function called peak. So you can set its parameters. Position, and then you overlay them. But this one is not obvious, is it? So taking this noise and overlaying the peak onto it. So this one will be scaling the peak down, scaling noise up. So the peak is embedded somewhere into that. So yeah, it would be nice to play around if something like this. For me, it would be issues of implementation. So if I want to make it available on the website, I don't know if each lab will cut it in theory. Yeah, MATLAB is a bit clunky that way. I'm not sure if we can just create APIs and HTML out of it, or JavaScript. I think last time I checked, I couldn't find a way to do it. But that being said, MATLAB is perfectly fine to use, and yes, a toolkit like that helps a lot. Yeah, this example, it will be interesting to see. So again, they're generating this noise, then this peak. So the peak is from, the noise is -1 to 1. The peak is 0 to 1. And then they just, add them together. But they scale the peak down by 5. So the noise should be, yeah, so it's that peak there, because they also negate. So it turns upside down. They scale the noise up and just plot it out. So yeah, it should be in the same position there. How come there's already, looks like there's already peak, slow wave something. Well, in the same amplitude as the noise. So the SNR will be a low signal to noise ratio. It seems like there's already something in there. I think it's just random. But then they take this peak and add onto that noise. And yes, my stuff. So you have this real data. This data is intracranial EEG. So I'm just repeating the same thing, but someone joined in, so I'll just do it again quickly. And let me know if there's anything you would like to discuss. But essentially the original data, yeah, it's this 16 channel intracranial EEGs. This is real data from real subjects. They do have epilepsy, these subjects. Those are animal subjects. This particular file didn't have any labels of seizures. So yeah, that second channel there is just a bit noisy. Otherwise, it's, yeah, this is real EEG. So I have to just take my word for it. Or go to ieg.org. You can download the data yourself and plot it in your own way. Then I have this this tool that essentially takes one of those 16 channels and plots its frequency response. So this is what it looks like. So I don't know if that's noise or or what, but that's how it looks like, and we can an example 10 seconds of it, and we can go into our synthetic EEG generator and essentially try and replicate the same thing. I don't know why people say, oh, but it's visual, your eyes are wrong. Well, no, they are correct. It's as good as it gets. So you can do this and try and replicate that this type of shape. And yes, there's a lot of render. I haven't thought about even doing this. So thank you to LinkedIn friend who was like asking about it, and I thought that might be an answer to it. Apparently the answer wasn't good enough because engineers and scientists, we want everything to be quantifiable and measurable. So in this case, sometimes you just have to rely on what you see. Anyway, I was just saying before that in some of these cases, you could replicate. So the MATLAB paper that this one, I don't know what they're doing here. They're going on a tangent, but this case is fairly clear. So if you want to replicate something like that, you don't actually have to inject spikes. These spikes could be also simulated using noise. So some noise will be just spikier. So if you did this and zoomed in on it, you can see it becomes much more. I don't know. You can add a bit of that if you want, and it becomes more spiky. Well, looks more spiky. I don't know. Yeah, depends what. Yeah, depends what type of spike. Same in this paper, they setting the frequency for the spike to be something. Generate a peak with frequency 5 hertz. So if this spike has a frequency of 5 hertz, 5 hertz would be, it's actually theta, not delta. So I can lower this one down. That would be like the DC in the signal, the lower frequency. And when increasing that, it will look more like spikes. If you're buying into it. If not, I don't know. So there was one. There was an interesting something there. So something like this. Just replicate the shape of your frequency response. And there is even another tool that shows you the spectrogram. And this will, the problem with this, I probably have to correct that. There is an automated signal selection. Did I have one where? Well, I'll probably have to add it where instead of, so in this case, it's automatically selecting a signal, and the algorithm is simply taking the largest amplitude. So if you look at it closer, it will just take take that mostly a second channel, just because it's noisier. So this frequency component there would be probably that spiky business here. I have to either make another tool like this that will have an option just to, instead of automatically selecting the channel, it will you could you could manually select which channel you want the spectrogram to be plotted for. Oh, cool. I might end it at this. And let me know if there's any questions. Don't forget to subscribe so I can create more of this goodness. And I'll see you next time.